Let's continue our discussion of buckling. We've covered previously the concept of buckling and looked at rigid members with springs, but now I want to apply it to deformable members. So before we can proceed, I need you to recall the beam deflection relationship. So we have, say we have a beam and we apply some type of transverse loading and that causes it to deflect. And if we call that deflection Y, do you remember the relationship between M and Y?
What's N?
M is the moment.
Oh.
So the relationship between the moment and the deflection.
Yes, it's second derivative of M over EI.
Okay, so M over EI, you said second derivative. Do you mean second integral? Good, very good. So if I want to solve in terms of M, we say M equals EI times the second derivative of the deflection. So we want to keep that in our pocket. Let's look at a column. We can put a pin at the bottom. We'll put a roller here at the top so that when we apply a load vertically, it can deflect downward, but it's not going to move laterally at that top. And we'll say that the Y direction is to the right. First thing we need to do is we need to assume that it has buckled. Remember I said you can never solve for the load that causes buckling with a straight member because you'll always just get that the member didn't buckle or didn't deflect. You'll get the answer in terms of it being vertical still. So you have to assume that it's deflected. So let's assume that this member takes a deflected shape. And now let's take a look at a portion of that deflected shape. So we're going to come in and cut here at X and at X plus delta X. And that gives us this little piece here. And we know that when we take those cuts, we expose internal forces. So we have some axial, or sorry, vertical force, not necessarily axial at this point if it's deflected, at X and at X plus delta X. Some horizontal force. And a moment. Okay, so those are our internal forces. And this dimension here is delta X. And this dimension is delta Y. Everyone okay with what we've drawn? Yes.
So you took a cut from there?
Yeah, I'm expanding this little section here, this little cut, or this segment of the column. And then I'm drawing the internal forces acting on the top and bottom of it. And I want to now take the sum of the forces in the vertical direction, so that'd be the X direction equal to 0. So I have R of X plus delta X as a positive minus R of X, and that has to equal 0. Those are the only vertical forces. So what I can see from this is that the vertical force is equal in both cases. And if I divide by delta x, this turns into dr dx, right, as delta x goes to 0. So not only are the two forces equal, the rate of change of the force is equal.
How do we do that, sir?
We took the sum of the forces in the vertical direction.
Okay.
And the only forces are this one and that one. If those two sum to 0, that means they must be equal. And therefore, the rate of change is 0. So essentially, this is just kind of a fancy way of saying that R is constant. That vertical force is constant. Not only is it constant, it's equal to P, right? Spoiler alert. If this is P, it's going to be equal to P. Okay, so we can also look at the sum of the forces in the horizontal direction, which I've defined as Y. And that tells us that V at x minus V at x plus delta x is equal to 0. And so that means that they have to be equal. The two different horizontal forces have to be equal. And if I divide by delta x, this becomes, oh well, and then of course I have to take the limit as delta x goes to 0, which I didn't do, or didn't write up there, but it's true. So taking the limit, I end up with negative dv dx equals 0. So the rate of change is constant. V is just constant. Okay. Now, hopefully a little more exciting result is going to come from taking the moment. Okay, so that's our setup. Now I want to take the sum of the moments at x plus delta x equal to 0. So I'm taking the sum of the moments at this point here on the bottom of the segment. So at that point, I have a positive moment, m of x plus delta x. Applied up above, there's a negative moment, m of x. The shear force at x plus delta x does not create a moment because it passes through the point we're considering. Same thing about the vertical force. But if I calculate the moment caused by v of x, I get a negative v of x times delta x. Then if I calculate the moment by r of x, I get a positive moment, and that's r of x times delta y. Now let's divide by delta x and take the limit as that approaches 0 and see what we get. We have 0 equals m of x plus delta x minus m of x over delta x minus v of x. The delta x crosses or reduces to 1 plus, now here instead of r of x, I want to plug in p, right? Because we know that this is equal to p. I'm going to say plus p delta y delta x. And the limit going to 0 says that this is dm dx, that's a change in moment over change in x, minus p of x plus p dy dx. That all has to equal 0. Now, if we just look at this first two terms, or rather this, is that circled portion somewhat familiar? That the shear is the derivative of the moment? Right? We already knew that when we talked about beams. So the only difference here is that before that wasn't the whole story. That was what was true if we didn't have an axial load. But now that we have an axial load, we have to account for the effect of that axial load being eccentric from the member. So once the member deflects laterally, it now is eccentric from any point on that member, hence it's creating additional moment. So let me ask you, what is the value of Vx in this situation? Good. Because if we were to take the summation at any point, we get that the shear at the top is equal to the shear at the bottom, or the horizontal force is the same. And so if we go all the way to one of the boundary conditions, we're going to see that there is no horizontal force because there's nothing causing a horizontal applied force. So yeah, they all are 0. They're all equal and they're all 0. So this gives us just that dm dx, so the derivative of the moment plus p times the slope is equal to 0. So we can integrate that and we get that m plus py is equal to 0. But now we want to bring back in the relationship between m and y. Right, when we first started this, we said that m moment is ei y double prime, so the second derivative of y. Oh, you know what? We're good. So that means that ei y double prime plus py equals 0. This is our big find. What does this look like? Do I hear it? Yeah, exactly. This is a differential equation. For those of you who didn't recognize it right away, if I divide by EI, I get y double prime plus P over EI times y equals 0. Now you see it? Ordinary differential equation, ODE, a good friend. You glad you took that class? Because now you know what's going on. Okay, so if this is an ODE, as you pointed out, the solution to it is a harmonic equation. So the solution to that is that y equals a cosine, what I'm going to say, little p x plus b sine little px. And little p is, of course, equal to the square root of that coefficient, big P over EI. That comes from differential equations. Okay. Now that we have it, we want to solve for A and B. And A and B have to satisfy boundary conditions. Everything we've done so far is general. It could have applied for any boundary condition. But at this point, we're customizing it to this pin-pin situation. And so we want to choose that y of 0 equals 0. So at one end, it has to equal 0. And at the other end, it has to equal 0. So when we choose this first boundary condition and we say that we plug in 0, this equation gives us y equals a times 1 plus b times 0 equals 0. Okay, this is gone, and it doesn't really need a y equals, does it? Actually, it's fine. We can keep the y equals. So what we find is that a has to equal 0. So this part of our equation does not exist in our solution. And then we come over here to the other one, and we plug in L, and we get that y equals 0, which equals b times the sine of PL. Okay. We can make this 0 in a couple ways, right? We can say that b is 0. What does that do? It means there's no deformation. What we've done is we've said that it doesn't deflect. So that's one solution, but it's probably not the one that we want, because the whole point was we want to know, what load does this equal? Does this become unstable? And if b is 0, we don't know. It could be any p. So we're not going to do that. The other option is that this has to be 0. So how do we make a sine function 0? PL equals 0, because the sine of 0 is 0. What else could it equal? Pi, which is the same as 180. What else? 2 pi, 3 pi, you get it? On and on and on. So it could equal any of these. I'm going to say if it equals 0, that's probably not a good choice, because L is a constant. To equal 0, P has to be 0, which then we're back to our load is 0. And it's like, well, now we don't really have a column at all. So if you 0 loading isn't a good answer to our solution. So really, the first time this will happen, the first time we can get it to buckle would be when pi equals PL. It would also, I need to be careful with my language. The first time it would deflect is when PL equals pi. It would also do it when PL equals 2 pi or 3 pi, but it's already deflected the first time. So what we're interested in is PL equals pi, which means square root of P over EI equals pi, which means our buckling load equals pi squared. Oh, did I miss something? I think I'm missing an L. There's an L here, right? Pi squared over L squared, and then times EI. Does everyone see that? That the first time it's going to deflect is when PL, little PL equals pi. Little p is square root of big P over EI. So you set that equal to pi, you solve for the load. This is your critical buckling load. That's when your member will deflect.
So then would we be able to solve for the
No, you can't actually solve. You never do no B. It's one of those mysteries that'll plague you till the end of time. But you can, if you know the deflection at a particular point along the beam, or sorry, the column, then you could solve for B. Yeah, or maybe it's for, maybe it doesn't matter, because for any B, it's going to do this. Sorry to disappoint. But the main takeaway is we have our critical buckling load. At this value of P, we can expect that it is unstable, and more than likely we will see lateral deflection. Not necessarily, but highly likely in a practical situation.